Just so you know, if you don't remember, you can minimize that go to meeting window by clicking on that orange white arrow. That's a toggle switch. It minimizes and maximizes it.
Oh, this, the thing on the side here?
Yeah, I don't know. I think maybe it minimizes automatically for the users. It doesn't for me, but I think it might for you guys. Yeah, if it's blocking your screen, you know, taking up too much of your desktop, you can minimize
it. Yeah, okay, I got it. Okay, so the first thing, looks like stuff with vectors, I think.
Okay.
The first one is, yeah, okay, so let u equal 2, -1. V equal 4, 2. And W equal 1, -3. And the first one of those problems is the absolute value of u plus v.
Okay, it's very straightforward. It's exactly what you would think it would be.
Okay.
Add individual components. In other words, u plus v is going to be 2 plus 4.
Okay, so is it just 6, 3?
6, 1. You said -1, right?
Yeah, but it's the absolute value of that, wouldn't it?
It's the absolute value of their combined?
Yeah.
Then it's 6, 1.
Oh.
You combine them first, and if we had any negative signs, we would turn them positive.
Oh, okay.
Hold on one moment. Look over into vectors. Vectors are a difficult subject. They used to terrify me, not so much anymore. I understand them a little better than I used to. All right. I mean, they can get really hard. All right, what else? I don't have anything in my book regarding absolute value. Well, a little bit, but okay, go ahead.
The next one is u times w.
U dot w?
Yeah.
All right, that's the dot product. Okay, and that's fairly straightforward also. It's this times this plus this times this.
Oh, so you add them together then?
Well, you multiply them and then add. In other words, here's what the dot product is. 2 times 1 plus -1 times -3.
Oh, okay.
Which is 2 plus 3, and it's a scalar. It is not a vector. And hold on one moment. Haven't had anybody doing dot products in a while. Okay, go ahead. Yeah, that's right. A dot product is a scalar. as opposed to a vector. It is not a vector.
Okay.
The difference between vectors and scalars are scalars only have one number that quantify them. Vectors have a number and a direction.
Okay.
So things that are vectors are velocity. It's not only how fast you're going, but what direction you're going. Force. It's not just how much the force is, it's what direction it's in.
Okay.
That's the primary difference between vectors and scalars. A scalar would be a temperature reading. A vector would be an airplane flying at 500 miles per hour due east.
Okay.
Okay. All right. What else do you have with these three vectors here?
Have 2u minus 3w.
When you multiply a vector by a scalar, in other words, when we multiply u by 2 and w by 3, just multiply each component. So this becomes 4 minus 2 minus 3 minus 9. Subtract the individual components. What do you get? You definitely get a vector, not a scalar. What is the vector?
That'd be 1 and 7.
Correct.
Okay, the next ones use different things here. Okay, so it says. Okay, so the directions are to find the component form and magnitude of the vector.
Good, because I was just going to say, if you hadn't have said something for another 5 seconds, I would have gone into my breaking a vector into its component form.
Oh, okay.
But go ahead, since you've got the problem, give it to me.
So it says let a equal 2, negative 1. B equals 3, 1. And C equals negative 4, 2. Oh, and there's also D. D is 1, negative 5.
Okay.
The first one of those is 3AB.
3A dot B?
No, it's just 3AB with like a little line over it. I think these are, the way that these ones are written, they don't have the pointy.
It's a cross sign. Like this.
Kind of, but there's like nothing written in between the.
Well, you have dot product and you have cross product. I can't tell which one you're talking about.
Well, the way that these ones are written, like they don't have the pointy parenthesis that you wrote down. It's like a round parenthesis. I think these are just points.
Ah, okay. All right.
I don't know if that'll change anything.
Well, actually it might. In other words, these are just coordinate points, like this.
Yeah.
Okay, let me change them all.
Sorry, I didn't notice that.
Well, that's when you talk about vectors, it's different. And how do they express 3AB?
It's just written 3 and A, B, nothing in between anything there.
Like that?
And then there's like that, there's an arrow above the A, B.
Ah, okay.
Yeah, like that.
Okay. What that arrow means is, well, let's first of all talk about vectors. Vectors have kind of a unique property. And that is that vector is the same as that vector. In other words, if the magnitude and the direction are identical, the vectors are equal. So maybe we have this vector that's between point A and B, and what we really want is to be able, instead of defining this vector by 2 points, like this problem does, we want to define it as always starting at the origin. And that way we can define it as one set of coordinates, not 2.
Oh, okay.
Okay. Well, in this problem, let's talk about what is AB. Forget the 3 for a moment. AB is equal to A minus B. It's equal to the vector minus 1 minus 1 minus another minus 1 is minus 2. That's plus 2. Excuse me. No, that's correct. In other words, let's graph this. Make sure that I've done it correctly. 2 minus 1 is right there. 3 plus 1 is right there. This is A, this is B. So to get from A to B, I've got to go to the right one and up 2. So I've got my signs wrong. It really is that. In other words, I could express AB, and instead of expressing AB between this set of x and y coordinates and this set of x and y coordinates, let's make it so it goes from the origin. And this vector I can call 1, 2. And that vector is the same as AB.
So is it going to be like the absolute value of
No,
one of them minus the other?
it's going to be the x-coordinate of B minus the x-coordinate of A for this number. And it's going to be the x-coordinate or the y-coordinate of B minus the y-coordinate of A for this number.
Okay. So would you always subtract the second letter or subtract the first letter from the second letter?
Yes.
Okay.
Okay. And then if you want 3AB, well, that's just multiplying a vector by 3. So that would be 3, 6. But this is an important concept in vectors, is understanding that when you have a vector between 2 points that aren't at the origin, it makes sense to express that as only one vector starting at the origin. This vector is going to have the same magnitude and the same direction as this vector. As long as this angle is the same, this angle theta, then they will have the same, it'll be the same vector. All right, what's your next question?
Yeah, this is AC plus BD.
All right, these are vectors. So to get AC, what would that be?
That would be C subtract for this, right?
C minus A. In other words, when we did AB, we did B minus A. The whole,
Okay.
and I did it wrong the first time. I did it A minus B. And then I realized when I drew my picture that in order to get from A to B, you got to go positive 2 up and, or excuse me, positive 1 over and positive 2 up. So it has to be B minus A. Well, AC has to be C minus A.
So that'll be -6. And 1.
It's 2 minus a minus
1. Oh, 3.
And BD.
That'll be -2 and -6.
Now add those two together.
That'll be -8, -3. Okay.
Another major thing with vectors is if that's a vector right there, starting at the origin, in other words, we've got it simplified, but what we'd really like to know is what is the x component of that vector and what is the y component of that vector? Well, if I create a triangle, the x component of that vector I can define with trig functions. What trig function includes the x component?
So is this like according to theta then?
Yeah. Cosine of theta equals x over 5. Right? From trig?
Yeah.
Okay. And sine of theta equals y over 5. Which means that x is equal to 5 cosine theta and y is equal to 5 sine theta. Now, let me give you an example. Let's say you have an airplane heading 45 degrees from east at 500 miles per hour. In other words, this picture right here.
Yeah.
With theta being 45 degrees. Now, if we have a westerly wind blowing against it at 50 miles per hour, what happens to the airplane? Well, if we break the airplane, the first step here is to break the airplane vector into its x and y coordinates. Well, I can see that x is equal to 5 times the cosine of 45 degrees, which is root 2 over 2. So the x component is 5/2 root 2 times 500. Hold on, I'm doing something wrong. What am I doing wrong? Cosine of 45 degrees equals x over 5. Therefore, x equals the cosine of 45 degrees times 500. Let's make sure we put the proper numbers on it. All right, that's correct. This is a number that's less than 1. So our x coordinate of that 500 miles per hour speed is going to be what? What's square root of 2 divided by 2 times 500?
Let me get my calculator out.
Okay. Even if you haven't gotten to this part of vectors yet, it's worth covering, because this is ultimately what you do with all vectors.
That's 353.55.
Okay, so that is in its effect, that's what x vector would be, is 353 miles per hour in an easterly direction. Now, what is the 500 times the sine of that? Well, it's the same thing, I know, because the cosine and the sine of 45 degrees are the same. So it would be 353 miles per hour in a northerly direction. Okay, you with me?
Okay. Yep.
Well, if we combine that with a 50 mile per hour wind that is going in a westerly direction, the only effect is on this speed. We can subtract 353 minus 50. So its new x direction is going to be 303 miles per hour. Its y direction doesn't change because that wind doesn't affect its vertical direction. It doesn't affect the vertical component. So its vertical component is still that. Okay, now we've got two new vectors. In other words, which way is the plane going now? Well, it's going more north than it would have been going. And the north component is 353. The easterly component is 303. Well, what's the new angle that it's going at?
That'd be the cosine or the inverse cosine of
inverse tangent.
Oh.
Because this is 353, that's 303.
Oh. Okay.
So inverse tangent of 353 divided by 303, what's the inverse tangent of that? It's going to be an angle greater than 45 degrees.
That is 0.86.
Put your calculator in degree mode for the moment.
Oh. Oh yeah, I'm in radians.
Yep.
Okay. Tangent.
With vectors, you tend to stay in degree mode, believe it or not.
Okay.
When you do calculus, you stay in radian mode, but when you do vectors, you tend to stay in degree mode.
Okay, this is 49.36.
So the plane, which was starting out at a 45 degree angle, headed in this direction at 500 miles per hour, is now going at a 49 degree angle And what speed is it going? Basically have to use either the Pythagorean theorem, or you can use either a sine or a trig function to figure out the hypotenuse of the new triangle.
Oh. So you would do...
Why don't you do, well, let's see. What's the easiest thing to do? We've got the sine of 49 degrees equals 353 over z. So z is, this is the easiest way, 353 divided by the sine of 49 degrees.
Okay.
Should be slower than 500 miles per hour.
Yeah, it's 467.7.
And that's real life vectors. This is what pilots have to do every single day, or at least computers that do all of this for them. But that's exactly the process they do.
Okay.
In other words, they start with a vector, they break it up into its x and y components, just like we did, because we always know theta. In other words, if you tell me a vector of an airplane, I know it's 500 miles per hour and it's going at 45 degrees east of north. That defines that vector. Now, if you combine that vector with something like wind that's working against it, I gave you an easterly or a westerly wind, which is against the direction that the airplane is going. If we turn this around and we make it an easterly wind of 50 miles an hour, then it's going to not only increase the speed of the airplane, but it's going to change the angle so that it's less than 45 degrees. But That's the way you do vector problems, is you break them into their components. There's another classic vector problem that is worth pointing out. To understand vectors. You have a rugby ball on the center of a playing field. You got 3 people tugging on it. This guy's tugging on it with 100 pounds of force in a north direction. This guy's tugging on it with 150 pounds of force at an angle of 10 degrees. This guy is tugging on it at a 45-degree angle. The ball is not moving. Everybody's force is equaling out such that the ball is stationary. So the question is what is the force that this guy must be applying to it? And the answer is you break each vector up, all 3 of these vectors, into their x and y components. You add all of the x components together, you add all of the y components together, and you get a resultant vector. In other words, my x components in this problem, all of my x components must be equal to 0, net 0. And all of my y components must be net 0. Because if they were not, that ball would be moving. In other words, if this guy were to double his force, this ball is going to go in that direction. Okay? So the fact that we know that the ball is stationary means that all of the x components cancel one another out. Whatever the x component of that vector is, it's exactly equal to the x component of that vector. Notice the x component of that vector is 0.
Oh, yeah.
That's 100% in a northerly direction. So I would say the y component of that vector is 100, and therefore the y components of this vector and this vector must be 100 in the other direction. And so that's how you solve this kind of problem.
Okay.
But the real essence is to break up a vector into its x and y components, add all the x components together, add all the y components together, and you get a net vector. All right, let's pick up from where your problems leave off.
Sure. Let's see. Okay, for this one it says.
Are we done with the A, B, C, D? Did we?
Yeah.
We did all of those? Okay.
Yeah.
Go ahead.
It says find a unit vector in the direction of AB. These are different things still. And a vector of magnitude 3 in the opposite direction. And A is 3, 1, and B is 5, 1.
They want what again? The unit vector?
Yeah. Find a unit vector in the direction of AB and a vector of magnitude 3 in the opposite direction.
Okay. So, AB. What would the component vector be for AB?
So that would be 2, 0.
Okay. Now, the unit vector for AB is this same vector, only it has to have a magnitude of 1. Well, what's the magnitude of this vector?
Is that Pythagorean theorem?
Yeah, it's the square root of 2 squared plus 0 squared. So the square root of 4, so it's got a magnitude of 2.
Okay.
Okay, in other words, if I were to graph it, it doesn't go in the y direction at all. It goes strictly in the x direction with a magnitude of 2. Well, they want this vector right here. The same direction, only a magnitude of 1. That's what unit vector means. And the way you get it is you take your vector and divide it by the magnitude. In other words, if I take AB and divide by the magnitude of AB, and this looks like an absolute value sign, but that's what it was before. It wasn't an absolute value sign. I wondered why you were giving me absolute value. It's not absolute value, it's magnitude.
Oh. Okay.
Magnitude is the square root of this squared plus this squared. So the magnitude of AB is 2. And when I divide that vector by 2, I get this vector, which happens to be that other vector. In other words, when they're talking unit vectors, let's say I have a vector like this. That's magnitude of 6. Well, there are times where you want to know what the equivalent direction vector would be, only with a magnitude of 1. And the way you get that is to take your original vector and divide it by the magnitude of the vector. And that's called a unit vector in the direction of v. Now, hold on. A vector u with length magnitude of u equals 1 is a unit vector. If v is not the zero vector, then the vector is a unit vector in the direction of v. Not quite sure why it's not a unit vector in the direction of u, because the formula they give is this. In other words, you take your vector and you divide it by its magnitude, and that's the unit vector.
Yeah.
In other words, the vector that I just drew on there, well, what would cause that to be 6? Well, if whatever these sides were, well, let's make it simpler. Let's make it 5. Now I know these sides are 3 and 4. So if I call this vector v, well, the unit vector would be this vector here with a magnitude of 1 in the same direction as v. Well, what is theta? Theta is like 37 degrees if you do the trick. In other words, this is a 3, 4, 5 triangle, and most people don't know these angles, but I happen to just because I'm a math tutor. Those two angles are 37 and 53 degrees, rounded off. Okay? So when I talk about u, it's the unit vector of v in the direction of v. That part of it right there.
Oh.
In other words, the unit vector is the same as our vector, only it has a magnitude of 1 instead of 5.
Okay.
Let's go through an example on that. I've got an example here that it might be useful. I'm going to define v as this. And it wants to know what the unit vector is. So what would it be?
So you do...
What's the formula? What's the general formula for the unit vector?
v over magnitude v.
Which in this case is?
Negative 3, 2 over 9 square root of 13.
Okay. So the u vector, the unit vector, is minus 3 over root 13, comma, 2 over root 13.
Okay.
If I were to give you that vector and say, what is its magnitude? You're going to square it, add them together, take the square root. That's going to be 9/13 plus 4/13 is 13/13. Magnitude of that unit vector is 1. That's the definition of unit vector. Its magnitude has to be 1. All right. What was the problem you had on unit vectors?
Yeah, Next one is A equals 4, 0. And B equals 2, 1.
What's the question?
Oh, it's it just has to find the unit vector in direction AB and the vector of magnitude 3 in the opposite direction.
Okay. So first of all, what is the vector AB?
That'll be -2, 1.
In other words, this vector is equivalent to this vector. This is in starting at the origin, though. Okay, so what is the unit vector for AB?
So that's -2, 1 over square root 5.
Which is?
-2 over root 5, 1 over root 5.
Yeah, and I'm not sure why, but I don't think we worry too much about rationalizing denominators here. In fact, I'm looking in the book, and it doesn't even worry about it. It gives answers with irrational denominators. Not sure why. In other words, if math has a convention that you shouldn't have irrational denominators, you'd think they would obey it. But this is the unit vector in the direction of AB. And you would prove it by taking the magnitude of this vector and discovering that it would be 1. Now, the other question was, what is 3 unit vectors in the opposite direction?
Yeah.
There's A. There's B. So there's my AB vector. And if I wanted the unit vector, maybe a piece of that, okay?
Okay.
In the opposite direction would be in this. And you said 3 times it?
Yeah.
So how do we get this thing to go in the opposite direction of this unit vector and 3 times it? It looks like I would have to go, instead of to the left, that amount, I would go that amount to the right times 3. So it would be -6 over root 5, comma, going down instead of up, this thing must be minus that.
Why is the one on the left still negative?
Good question. I was wrong. It's positive.
Oh, okay.
In other words, the original vector, I was going to the left and up. The new vector, I'm going to go to the right and down.
So when you're finding the opposite direction, do you just change the signs then?
Yeah, I guess so. I wasn't, yes. I didn't realize it was that simple until you corrected me.
Okay.
Okay, what else?
Let's see. Find the direction angles of U and V and the angle between U and V.
Okay.
The first one is U equals 4, 3.
And that is a vector, correct?
Yes. And V equals 2, 5.
What was the question?
Find the direction angles and the angle between U and V.
Okay. So, how would I express that? In other words, I've got two vectors here.
Yeah.
Can I combine them into a single vector?
Do you just add them? Oh, okay, so it's like with the points
Now,
then?
hold on. Let's see. If I draw V, or U rather, I got to go over 4, up 3. So that would be U. And if I draw V, I got to go over 2 and up 5. So that's V. The first question was what? What is...
First one is the direction angles of U and V.
All right, let's talk about that first.
Okay.
In other words, they want this angle theta and this angle alpha.
Okay.
Well, if I look at U, what are my x and y coordinates?
So that's 4 and 3.
What's that angle?
That is inverse tangent of 3 over 4.
That's 37 degrees. Round it off.
Okay.
Okay. Now let's look at vector V. What is the entire angle there? Inverse tan of what?
Oh, that's inverse tangent of 5 over 2.
You're going to have to look in your calculator for that. I don't know what that is.
Okay. That's 68 degrees.
And that's the whole angle. In other words, that's the angle from the x-axis to that vector.
Yeah.
So we've answered the first questions. Now they want the angle between the two vectors.
Yeah.
There happens to be a formula for that.
Wouldn't you just add the two angles together and divide by 2, or is that something else?
Actually, it looks like you can just take alpha minus theta.
Oh.
However, there is a formula for this. Not quite sure why, but there is. I'm trying to find it. Second. My book pages fell apart. Second. The angle between two vectors. What's going on here? Hold on a moment. The cosine of that angle equals the dot product of the two vectors divided by the magnitude of the two vectors. What were my vectors again? I'm sorry.
U is 4, 3, and V is 2, 5.
So, what is the dot product? What is U dot V?
How do we do the dot product again?
Multiply each component and add. In other words, 4 times 2 plus 3 times 5.
Okay, so that's 8 plus 15. Oh, you got it.
Okay. Now, what's the magnitude of U?
So that's 16 plus 9 square root. Okay, so that's 5.
Okay, and the magnitude of V?
Square root 29.
Okay, so that's the cosine of theta. So theta is equal to the inverse cosine of that quantity. 23 over 5 root 29. Now, root 29 is going to be 5 and change, so we are taking the inverse cosine of a number less than 1, which is good to know. So what is that?
Um, 0.85.
In degrees?
Yep. Oh, wait, I didn't do the inverse cosine. Okay.
So you want the inverse cosine of 0.85.
Okay, so that's 31.3.
Okay. So that's the angle between the two vectors. And when we did it originally, we had that vector at 37 degrees. We had that vector at 68, if I remember right.
Can't remember the second one, actually.
Yeah, it was 68. And notice the difference between those two angles is that.
Is that a coincidence, or?
No, it's not coincidence. It's as it should be. I'm not quite sure why they give you this more complicated formula, but if you had a vector u and another vector over here, v, and you wanted the angle between them, then you can use that formula as opposed to the way we did it. The way we did it the first time was we figured out theta and we figured out alpha, and then we subtracted the two, which certainly should give you the same answer, and it does. In other words, when we did it the first time, we got 31.3, and when we did it using their formula, we got 31.3.
Huh.
Using their formula might be easier in problems like this, where this angle isn't that easy to figure out from V alone.
Okay.
You could always figure out this reference angle there quite easily, but then you'd have to find the supplementary angle to find the bigger obtuse angle. And yeah, it's hard to see where it's easier using their formula, but there must be some reason they give it to us.
Okay.
I mean, you know what I'm saying? In other words, when we get to three-dimensional vectors, then it's probably necessary to use that theorem, the angle between two vectors. What makes two vectors orthogonal to one another? What does orthogonal mean?
I don't know.
Orthogonal is pretty much the same as perpendicular.
So they just make a 90-degree angle then?
Yeah, and
Okay.
what makes that 90-degree angle is if the dot product equals 0. In other words, two vectors are orthogonal if and only if u dot v equals 0. So if I had this vector u, like I've drawn here, and the other vector v, and I wanted to know whether that's a right angle between the two, just take the dot product of u dot v, and if it's 0, that's a right angle.
Okay.
Now when you get into 3 dimensions, you could have a vector coming out from the page that would be orthogonal to both of those vectors. And that has to do with cross product. And I don't remember exactly. God, I hope you haven't gotten into the projection of u onto v. Have you had that yet?
Yeah, but I mean, we're just doing a review right now, and
Okay. Well, that's tough. That's a tough one.
yeah.
The projection of u onto v involves basically changing your axis so that when you have this situation, you're going to rotate the axis so that it lines up with your vectors or something like that. I've always had a tough time with it, actually, to be honest with you.
Okay.
I could go through what I'm looking at in the book, and that might help, but probably not the most valuable thing for us to review. What we're doing is probably the best. But
Okay.
got any last questions?
No, I think we can. I mean, the review kind of goes through like a whole bunch of units, so we can pick up next week as well, because the test is only in a few weeks from now.
Okay, so this is for your final.
Yeah.
Okay. I will talk to you next Tuesday night.
All
All
right.
right, Daniel. Bye-bye.
Bye.